Exciting times. Carbon-13 NMR. So you recall anything that either has an odd mass or an odd atomic number. Carbon at atomic number 6 and 12 is not active, has no magnetic moment. Carbon-13, that odd mass number, gives it magnetic spin. Unfortunately, only 1% of carbon-13 is abundant, and to add insult to injury, the gyromagnetic ratio of carbon-13 is 1/4 that of a proton. But with technology, carbon-13 was never available like in the 70s, early 80s maybe. Wasn't until the advent of a technique called Fourier transform. And a Fourier transform takes something that's like, I like to think of if you hit a hammer on a bell and it rang and you had an oscilloscope and you'd see it ring and it would die out over time. And so you'd have amplitude, just like, so you had a microphone, just like a voltage from a microphone. Or you can even imagine a guitar, electric guitar string, and time on this axis. And if you Fourier transform this, you get a peak representing the frequency of this wave. That's how I like to think about it. So instead of scanning various radio frequencies and seeing absorptions, a radio frequency pulse is given. It excites these nuclei, and they give off a signal when they decay down, and then that is detected, and Fourier transform is done on this free induction decay waveform, and a spectrum is generated. You can expect that. So different carbon atoms, depending on what they're bonded to, have different amounts of de-shielding, and is somewhat similar. Alkanes are fairly shielded, and then things move down. And you can see here an interesting parts per million, just like with the proton. But the proton, we went from like 0 to 12, and everything fit into here in that window. Here we go from 0 to 200. So here's a table of approximate chemical shift values for carbon-13. Most of the values for a carbon atom are about 15 to 20 times the chemical shift of a proton if it were bonded to the carbon atom. So let's look at this. Looks like a biochemical molecule to me of some type. 1, 2, 3, 4, 5. 5 protons. And what do we end up seeing? 1, 2, 3, 4. Not seeing the 5th. Maybe a couple of these are on top of each other and I really can't distinguish them. But what's more important is how many carbons do I have? 1, 2, 3, 4, 5. Let's go up here. 1, 2, 3, 4, 5. There's all my carbon atoms. What's this thing? A lot of these things, if they're solid at room temperature, we need to put them in solution. So here's a common solvent, deuterated chloroform. And there is a carbon, and so that shows up. It's fairly easy to recognize. So what are some of the differences? Resonance frequency is about 1/4 of hydrogen. Peak areas are not proportional to the number of carbons. Carbon atoms with more hydrogens absorb more strongly for some reason. So if a carbon-13 was adjacent to another carbon-13, it could split that signal. But available at only 1%, we never see that. It is unlikely that a carbon-13 would be adjacent to another carbon-13. So signal splitting by carbon is negligible. Here's something very interesting. Carbon-13 will magnetic couple with attached protons and adjacent protons. You can put a little asterisk here. I don't normally see that a whole lot. These complex spitting patterns are difficult to interpret, and no, they're not. It helps, and you'll see. That's just to do some reverse psychology on you. You think it's going to be hard, and it's not going to be hard. To simplify the spectrum, protons are continuously irradiated with a broadband noise so that they rapidly flip in the magnetic field, makes their signal disappear. The carbon nuclei see an average of all the possible proton spin states. Thus, each different kind of carbon gives a single unsplit peak because carbon-hydrogen splitting was eliminated. Now, the nice thing is you can do 2 experiments and have it eliminated and have it not eliminated, coupled and decoupled. So here's a decoupled spectrum. Looks like something we've looked at. 2 singlets for the protons. What about the carbons? I got 1, 2, I just only have 3 carbons. Where do they show up? Here they show up. This thing here is probably a liquid. All we have to do is add a little TMS. And we don't really look at the heights to figure anything out. Let me see if you're paying attention. Why is this peak higher than this peak here? Right, it said for some strange reason the more hydrogens make them absorb more. Yeah, so maybe that can be a clue, maybe not. So now we have off resonance where we let those protons go ahead and couple. And that might be nice because we see this peak corresponds to that carbon there. And this carbon has 2 electronegative elements stuck to it, de-shielding it more than any of these others. This one only has 1, this one has none. That's why they show up where they are. Well, look at this. Here is the TMS peak. And when I look at this TMS peak, I see a quartet. And so if the signal is split by 3 hydrogens, N is 3 plus 1 equals 4, and I see that quartet. Here's a quartet. Look at this thing. This carbon signal will be split by those 2 hydrogens, and I see a triplet. So I don't know why that other slide said that this was bad or complicated. Carbon-13 nuclei are split only by the protons attached directly to them. This thing's not going to be split by those protons. So there's a difference between the carbon-13 NMR and the proton NMR. The N+1 rule applies. A carbon with N number of protons gives a signal with N+1 number of peaks. So I think a carbon-13 spectrum gives you lots of information, tells you what type of carbons by where they're at. And in the off-resonance experiment where we let the protons split the carbon signal, we get to see how many protons are attached. So a lot of similarities interpreting a proton NMR spectrum and a carbon-13 NMR spectrum. The number of different signals indicates the number of different kinds of carbon. Very similar there. The location, chemical shift, indicates the type of functional group, how shielded or de-shielded it is, what's attached there. The splitting pattern of an off-resonance decoupled spectrum indicates the number of protons attached to the carbon. So here we see the coupled and decoupled. It always seems a little backwards to me. I'm just gonna try not to point attention to it. But how many carbon environments do I have? How many carbon atoms? 1, 2, 3, 4. And just like in the proton, if my carbon atoms are equivalent, I don't see any equivalent here. This thing's kind of asymmetric. You know, I have 2 methyl groups, but this methyl group is right next to a carbonyl carbon, so these carbons are in different chemical environments. This one's definitely in a different chemical environment. And this one's, you know, in between those 2. We could probably predict chemical shift of the carbons just in a similar way that we would with the hydrogens, meaning this one's furthest downfield. That's this one here. How do I know that this one's here? 3 hydrogens, I should see a quartet. And there you see a quartet. This thing way over here, a singlet, no attached hydrogens, and this is the most de-shielded, so furthest downfield. So this thing here, 2 hydrogens should see a triplet. And this one evidently must be that proton there. 5 carbons. 1, 2, 3, 4, 5. Do I have 5 signals? 1, 2, 3, 4, and 5. Here's where we might kind of like going to the decoupled, or the one with no peak splitting, because this kind of looks like a mess. So the same principles that we use in the proton NMR, we use in the carbon-13. This x-axis just blows up wider, and we can turn coupling on and off. So I started talking about MRI at the beginning, nuclear magnetic resonance imaging, non-invasive diagnostic tool. This was not an original idea. I came up with nuclear is omitted because of the public's fear that it would be radioactive, and the computer puts it all together, and you can see tore ligaments, bad heart valves, tumors, arthritis, scar tissue, all kinds of great things. So now we just have carbon-13 spectrum here in front of us. So what's the first thing I do when I go to solve a NMR spectrum problem, when I know the molecular formula? I see degrees of unsaturation, right, 2n plus 2, 16 plus 2, and I got 8. That gives me 10, 5 degrees of unsaturation. And let me just bring something up here. Only carbons from, what are these, 60, 70, 80, 90. All right, so carbonyl carbons. Do you think I have a carbonyl carbon? Look at this thing, a singlet. So this is probably carbonyl carbon. What else do I have going on? Alkanes, 0, 10, 20, 30. Probably have an alkane there. Alkynes, 100 to 150. 100 to 150. Well, look, I got 137, 133, 128. Got a bunch of double bonds. Might have a ring. There's 1 degree of unsaturation. So let me just minus 1 ring, perhaps. Minus 1 from carbonyl carbon. What does that leave? 3 double bonds. So 3 double bonds and a ring get me to 4 degrees of unsaturation. Let's attach the carbonyl carbon. How many carbons do I have now? I think I have 7, right? 1, 2, 3, 4, 5, 6, 7. Got to attach another one. Now, how many hydrogens do I have? I have 1, 3, 4, 5. 5 from 8 leaves how many? 3. Let's see if that looks fairly reasonable. How many carbon NMR signals should I see? I'm going to go 1, 2, 3, 4, 5, 6. I might count these as being chemically equivalent. 4, 5, 6. I only have 5, right? 4. Well, this is the structure. Let's just rationalize. Here's the singlet. Here is another singlet. So that's going to give me a singlet. This singlet here corresponds to that one. The quartet. This is the 198. So now the rest of the doublet, a doublet. How many doublets do I have? They're not right enough. Why aren't all 3 of these equivalent? They probably are. That's probably why. Gold star, Caden. That makes it work a little better. If these are my 5th carbon here, notice should have doublet, 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 doublet. There's definitely a line of unsymmetry here. My quartet. Here's my other singlet. I'm gonna call this the 130 doublet, and I'm gonna call this the 128 doublet. The 128 doublet, not quite as shielded as this, and now I should have all my signals. Where would make that go? That's my 137, the 128 doublet. I think that looks pretty good. We have time just for one more exciting structure. I may not be dyslexic. Given that compound X has a molecular formula of C6H8O2, gave 2 peaks in its carbon-13 NMR spectrum at 27 parts per million and 208 parts per million, but just 1 in its proton NMR spectrum provide a structure. I'll give you opportunity to think about that real quick. Oh, I was hoping one brave soul had it figured out. Champion, right here. Michaela has solved the structure. What? You thought it was wrong. Be confident in yourself. Well, 6 twice is 12, 14, minus 8. What is that? 6 divide 2, 3. Well, and this should stick out like a sore thumb. What group had this chemical shift for carbon-13? Carbonyl. And each one of those, if I have 2, I would go minus 1 for each one of these. And so that gave me 2. And if I subtract another one, I have 1 degree of unsaturation left over. Do you want to do a double bond or a ring? So one other thing we have going on, it just has 1 proton peak, meaning every proton is equivalent with the other. Right, so we're gonna do a ring. So 2 carbon-13 peaks. We have 208, 208. This is down in the alkane type situation. So 37, 37, 37. Just 1 peak there. That's gonna be that thing there at 2.5 parts. Out of time. I'll see you all Friday.